Today's lesson says review of exponential models. To which you might reply, review? I don't know that we've done any exponential models. And the answer is, you're right. I stole this lesson from advanced functions. And let me tell you how I use it in advanced functions. Is I use it to go, this is what you're supposed to know from grade 11. Because often people don't remember it. Okay? So don't let that intimidate you. This is what I think you're supposed to know in grade 11. You can just cross out the review. Yeah? And you're going to see this exact lesson again if you have the class with me in advanced functions, because I teach this exact same lesson to remind you about exponential models. Now, having said that, there is one question that will be very difficult for us to do. I don't mean like difficult like we won't know how to do it. We'll be annoyed by what it takes to do a certain question. And that's what they learn in advanced functions. So you'll get a preview of advanced functions here in the middle of all this, okay? Don't worry about all that. That's just some details that might catch you off guard with the name of this lesson and when you show up in advanced functions. It's actually pretty straightforward here, what has to happen. The simplest version of the equations will come today. So I made up a silly example to try and help you remember when you're doing exponential models. An exponential model essentially means there's some real life situation that we're going to use our equations to get the answers. That's all. So there's a model we will fit to the real life situation. So here's the real life situation I made up. The number of cockroaches in Mr. Todd's house is 5. I've never seen a cockroach in my house before, actually. I'm not even sure I would know what a cockroach is, but I've heard that this is a horrific insect to have in your house in certain parts of the world. So I've heard of them before. Mice. We get mice in our house often. It makes Mrs. Todd very unhappy. So I'm the mouse hunter. Anyways, the number of cockroaches in Mr. Todd's house is 5, and that number doubles every week. How many cockroaches will there be in 10 weeks? Now, if you're a really skeptical person, you might be like, how are you going to count the cockroaches in your house, Mr. Todd? Well, actually, biologists are pretty good at this type of thing. It's not that hard to do. I'll use fish as an example. If you go to a lake and catch 5 fish and put a little tag on them, a little yellow tag on their fin, ka-trink, and you let them go. Then you wait a week and you go out and you catch 10 fish and you see how many of them have a tag. You can pretty easily do some multiplication and figure out about how many fish are in the lake. So it's not that difficult to do. I'm simplifying the process. They do a lot better job than what I'm saying. But it's not that hard to count what's in there by just sampling how many are in there and tagging a few, and then come back in a week or so and see how many tagged ones you get.
Wait, what's the math for that one though? Because you have to like.
If we did enough, and 5 is not enough, by the way. 5 is not enough. I'm just using 5 as an example. If I caught 5 fish and only 1 was tagged, then I must know the number of tagged is 1/5. Yeah. So I just multiply how many I tagged by 5, and now I know how many fish, approximately. Will it be a perfect measurement? No. Should I sample all over the lake? Yes. Of course they're doing much better than what I'm describing.
And they probably tag like 10 out of.
Yeah, well, they tag loads, loads of fish, and do it multiple times. So it's not random. Yeah. So, but not hard to do. But I don't want you to get distracted by that. I'm not tagging cockroaches in my house. Let's get back to the example. The number of cockroaches in Mr. Todd's house is 5, and that number doubles each week. How many will there be in 10 weeks? Well, there's multiple ways to do this question. I'm going to show one easy way to do it that takes a long time. And then we'll see if we can't do something way better with a fairly simple equation. I started with 5. How many will I have after 1 week? If the population is doubling each week. 10. Right. 10 is right. But I'm going to write 5 times 2 because I'm up to something, okay? Which is 10. Yeah? So outside is the number you're thinking, and inside is what I'm thinking to try to prove something awesome to you, and it will not take long to figure out what's happening.
How come you don't start at 5?
Because 5 is what it started with. If you want, actually, he's not too far off base. Maybe this table should have that on it as well. At 0 weeks, there's 5. After 1 week, now it's doubled to 10.
That's impossible. You can't have 0 weeks.
Right now would be 0 weeks. Like if right now I went to my house and said how many cockroaches are there, line up cockroaches, and counted them, and there was 5, that would be, I'd have set that as times 0. Then 1 week is after 1 week has passed. It's an important distinction, actually. It may sound like a silly question, but it's not. It's an important distinction. Like, what is week 0? And week 0 is usually, we set week 0 to be right now. And then 1 week is now 1 week has passed. So after 1 week, there'd be 10 cockroaches. Well, how many would there be after 2 weeks? 20, but that's not what I'm going to write. I'm going to write, take your 5 times 2 and multiply it by 2 again. And that gives the 20. And I'm going to do something that actually might completely pierce the whole lesson. What I write next might be enough for you to go, I totally see what you're going to do here. Maybe not. That's why I'm doing a whole bunch. 5 times 2 squared. That's how many there are after 2 weeks. And no reasonable human would do this with exponents if it was only for 2 or 3 weeks. But look over here. What I'm going to ask in just a second is how many in 20 weeks. And we're going to need a better plan than just a table of values. The table of values is fine. I like the table of values, but I don't know. So that's what I'm up to up here, to see through my teaching here, is to see why I'm writing it like that. So how many cockroaches will there be after 3 weeks? He's already with me. Yeah? He's already switched over. Because most people would say 40 because they just double it and go, why not just do it that way? I'm like, well, it works. It's fine. There's nothing wrong with that. It's just if we have to get up to a large number of weeks, this is going to take a while. But the answer really is 5 times 2 again, and then times 2 again, which is 5 times 2 to the power of 3. And hopefully now you're not going to write all the 2's anymore. And maybe for the first time you have some respect for exponents, where you're like, hey, if you're going to multiply by 2 a bunch of times, I don't want to have to write 5 times 2 times 2 times 2. That's why exponents exist, because somebody was doing this kind of math and going, enough. If we got to multiply by 2 4 times, I'm going to write 5 times 2 to the 4th. And I know that answer is 80, but I'm actually losing interest in this outside number now. Personally, I'm like, I don't really care that the number's 80 anymore. What I care is I've got a great way to find the number without doing the table. 5 times 2 to the 5th is the next one. 5 times 2 to the 6th is the next one. I've got a calculator. I can punch them in at any time and find what these answers are. But this is a way to get to the answer without using the table the whole time.
Won't it be like a billion?
Oh,
Because like
big, giant numbers we're going to get here.
You hear that, like it's like, would you rather $1 million or like a penny that doubles every
Yeah, I
day?
did that example in this class one day and talked about how big these things get.
It's like 5 million.
Yeah, exponential growth, it's just huge. So I can finish this table off, 5 times 2 to the 7th, but I hope you're bored with the table now. As you're writing 5 times 2 to the 8th, 5 times 2 to the 9th, I hope you're like, okay, can you get to the point now, Mr. Todd? And the point is this. What if we wanted to know the number of cockroaches after 20 weeks? I hope you're not going to say, oh, let's just continue the table down. If you are saying that, then I'm like, okay, let's talk about how many there'll be after 52 weeks. And hopefully you're like, okay, I give up. The answer is simply 5 times 2 to the 20. And I wrote whatever that is. Now I'm going to get sidetracked just a little bit because there's some trouble with large numbers. I'm going to punch this number in and see what I get on my calculator, and we should talk about it just a little bit, about what the calculator is going to do with very large numbers. Because it can mess you up in other classes.
I don't think it goes more than like 10.
You're right, there's a limit to this, to what the calculator can handle and display normally, and I think this breaks the limit. 5 times 2 to the power of 20.
It's going to be like an east, like...
It's 5 million.
Okay, so this was reasonable. Reasonable. 5, 2, 4, 2, 880. 5,242,880. Okay, future biologists and chemists, this doesn't really play out like this. At some point, the cockroaches realize there's not enough food in my house for 5 million cockroaches, and the population starts leveling out again. So we're not quite there yet. We're not quite ready to send you off to take biology at university, because we got to talk a little bit about limiting factors and how many cockroaches can legitimately live somewhere. Okay? So we're just doing a model of what could happen, but there's certainly more factors involved. In fact, it's so complicated actually that somehow the animals know without even thinking about it. For instance, if a rabbit gets pregnant, when there's lots of food around, sometimes they'll have 5 or 6 rabbits, baby rabbits. If there's not much food around, they often have 1 rabbit. Somehow biologically they know. Not much food around, don't have many babies, right? Okay? I'm not sure humans have this ability, but animals certainly do. They know what to do. All right. Now let's just talk about bigger numbers. I don't have it in this example, but I just want to talk about if you went to, say, 100 days, something whacked happens to your calculator, and every calculator is different on what it writes, because it runs out of digits is what happens. And it'll write something like this with a little e there. And what that means is 6.33 times 10 to the power of 30. That means multiply by 10 30 times. So if you want, this is 6, 3, and 29 zeros is what that is. It's called scientific notation. You might not have run into it yet, but I just warn you about it, so if you do run into it, you don't write 6.33 and go, what, there's 6.33 roaches? How is that possible? My calculator must be broken. No, your calculator's telling you something different. It's saying, I've run out of digits. But if you're willing to use scientific notation, this is what's going on, okay? So you'll run into scientific notation as you go along. And if you see this crazy notation, in my class, you can immediately just call me over and we'll talk about it and see what we're dealing with there, okay?
So what is
This is 6.33
okay.
times 10. I use a little e to say times 10 30 times. So it's
Times
10.
30 or 30
no,
times?
times 10 30 times. The exponent on 10 is 30. Some better calculators actually show, does that Casio one actually show a little times 10 to the 30? Yeah, it does. So the better ones actually show what they're talking about here. So this is this isn't 6. This is a very big number. It's a number that starts with a 6. I'll try to write it because you seem curious. So I'll try and write this number.
So it's like adding.
6. 8253001. 8253001. Here's the actual number. Now I got to add zeros. How many zeros? I got to get up to 30, is it? Yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 21, 2, 3, 4, 5, 6, 7, 8, 9, 30, something like that. That's what your calculator's trying to tell you, is it's really big. So when you see this on your calculator, don't go, oh, something's wrong, it's broken. Just go, we haven't really learned about that. You'll learn about it in chemistry, and you'll also learn about it in physics, and it's not that difficult to deal with, actually. It's looking difficult here, but it's not really a big problem. People who take those courses aren't overwhelmed by this, really. Okay. Anyways, I wanted to warn you about that, because it can come up. Anyways, that's not what we're trying to accomplish today. What we're trying to accomplish is, can I come up with an equation that covers all of these situations? And the answer is yes. Yeah. From now on, the general model for this we could use would be y equals 5 times 2 to the x. And I really want to talk about this because that equation right there is all we're going to use today. Now, the 5 might change, and the 2 might change, but that's the only equation we're going to use all day. Okay? Now let's just talk about what it means here. The general equation then is y equals a times b to the x. We don't even have a c to deal with today. And there's reasons for that. But generally speaking in word problems, you don't need a c. The a and b will be enough to handle the situation. And it's this simple, by the way. The a is the initial or starting amount. So if they give you the initial amount, you just fill it in there. And this time it was 5. I gave it to you. Most exponential questions just tell you the start value. They say, you're starting with this much. You usually know what you're starting with. That usually word should scare you. It should be like, well, usually, is it sometimes? Yeah, well, let's just let that happen. We'll just let that play out. But for now, most questions just tell you, here's how much you start with. Then this this base is the growth factor. And this growth factor will be the main problem today, is deciding what growth factor it is. This one was doubling, so finding out that growth factor of 2 wasn't complicated. So if it's doubles or triples or quadruples, it should be easy to come up with that factor. But other questions might be a little bit more complicated, and we'll see that in a minute. So we now have a general model right here, y equals ab to the x, for these type of situations where the amount grows, where the amount something doubles, triples, quadruples, and then I wrote or whatever. And the or whatever is what should worry you about this lesson, because there is some little bit of difficulty coming in that growth factor. Well, I'm going to use that about, I don't know, I forget how many times in this lesson, a bunch of times. Some notes before we start though, right? You don't have to copy any of these down. There's a fancy box with it in there, and they put a C and an A in there. You can use A and B because that's what I've been using, but generally, listen, if you're thinking biology, chemistry, generally they use it like this, CA to the X. And there's reasons why they switch the letters, and those reasons really don't matter to us right now at all. Yeah? So you can use AB to the X, so I'm going to put that right beside here. You can go ahead and use Y equals AB to the X, or you can use CA to the X, and it's the same thing, okay? So I'll talk about that more as we go on. Now, this says A greater than 1. A doesn't have to be greater than 1 unless it's going to be growth. If this thing's going to increase and get bigger, that A value will be greater than 1. Okay? If that confused you, just hold on. I'm going to deal with those in this lesson. The quantity A can be called the growth factor. It's not always called the growth factor. Some textbooks call it something different. And the quantity C is the initial amount or the population. In this case, my cockroaches had population 5 to start with. There are only a couple things to remember here. The growth factor does not have to be a whole number. The fact that the cockroaches doubled once a week, if you really thought about it, you're like, why would they double every week? Does like every Sunday night at midnight they line up and go, boop, and they double? Like what? That's not really what happens, okay? So that growth factor doesn't need to be a whole number of 2. That was just the convenience of me making up a cute question that worked out nice, okay? It can be any number greater than 1 unless it's exponential decay, but I'll deal with this later in the lesson. In fact, I'll sneak it up on you. All of a sudden you'll notice that I did a decay one in the middle of it. The cockroaches could have had a growth factor of 2.3, 7.11, or something strange like root 7. We won't do too much of that, but just in the real world, cockroaches don't try and double every week. They'll double exactly how often they want to, and that's it. They're not dictated by my little table. Yeah? And then it said we may have to work backwards to find the growth factor or initial population. Let's let that sneak up on us too. It's not that bad to do those things, but let's let that sneak up on us too. Right into what I think is a fairly straightforward question, now that I've taught that first example. And then I'll ramp it up from there. A certain bacteria triples every hour. If there's 30 bacteria initially, find the exponential model. So you start off by writing y equals AB to the x, or if you're feeling very grown up and cool and you want to switch over and use y equals CA to the x because somehow that apparently is the cool way to write it in biology and chemistry, you can use either one. It doesn't really matter. But the two things we need for the exponential model is the A and the B, and is it already entrenched in your memory what these two things do? That's what the opening silly cockroach example was supposed to do, is make you go, oh, I know what the A's and the B's are. What does the A represent in these situations? The initial amount, which in this case was 30. As promised, they often just give you that. They just hand it to you. They say, this is the initial amount. Because in a lot of biological situations, we'll know the initial amount. We can just count them and say, here's how many there is. Then B is the growth factor. This time it's 3. Does it have to be easy like that? No. That's just my warm-up example. And many examples, it will be easy, because they'll say it doubles or it triples or whatever. That's the end of the exponential model. I now have an equation I could build a table with. I could graph it. I could do whatever I want. But in this question, they say, find the population after 7 hours. So after 7 hours, my population will be y equals 30 times 3 to the 7, which I can just punch into my calculator. 65,610. This is why you can't leave the chicken on the counter after dinner for 3 hours. Bad things happen in a fast hurry. You got to get it in the fridge. And then this 3 number in the fridge drops to like 1.001. There's still bacteria growing, but it happens very slowly, so you can have a few days to still eat the leftover chicken. That is almost a perfect explanation of what's happening. That's pretty close to exactly what you deal with, and why chicken, you just can't leave it out. Beef, well, it's not so bad, but chicken, fridge. So the bacteria slow down. Yeah? 65,610 bacteria if we were getting all upset about units. Now, see this bold one? This is the question we cannot do in grade 11. Not without some serious playing around. This is what you will learn in advanced functions, because the difference is now I get this equation. 1,000 equals 30 times 3 to the x, and it's my job to figure out what the x is. We teach you a way in advanced functions to do this, but if this appears in your homework, and if it is in your homework, it like appears only once. Yeah, where you'd have to go to your calculator. Hang on, Kyle. And you'd have to go, okay, well, I don't know. It's got to be a lot more than 7, does it? No, that, oh, 7, it's already at 60. So I know 7's too big. Okay, so how about 30 times 3 to the 6th? I hope you think this is insane, what I'm trying to accomplish here. To just get the answer by trial and error. 21,000, too big. It must be smaller. Go back and change this to a 5. 7,290, it's smaller than 5. Go back and change it to a 4. And you might think this is insane, and it is insane to try to do it this way. But would you agree that given enough time, I could Price is Right this thing? You know what I mean by Price is Right? Higher, lower, higher, lower. I could play around until I eventually got the answer. And like I say, I think there's maybe one in the homework that forces you to do this. 3.5, is that too small? Oh, I'm getting close now. Some of you might be nerdy enough like me where you actually think this is pretty fun to try to come up with this. 3.1, ooh, it's bigger than 3.1.
I feel like there's an easier way that we should talk.
There is an easier way. It's called logs, if you want to know what it is. Ooh, 3.2, pretty close now.
I got 0.1919.
1919? He's way faster than me on the calculator. 1919.
It was like as close as I could get.
Pretty close, okay? So we'll say trial and error. I'm not putting any trial and error on your test, by the way. That's not going to happen. But there might be one in the homework you can play around with and try this 1 or 2 times. X equals, and I put a little dot over top. Have you ever seen that before? With a little dot over equals? Means it's about, you know, I'm not claiming it's exactly right, but it's approximately, what do we say? 3.1919. There's something called logarithms. You might not have heard of it, and it'll come up in chemistry class, but logarithms will allow me to solve this problem without trial and error, but you don't learn about them until grade 12. They're not that hard, but we ran out of time. There's not enough room in this course to teach logarithms as well. You got even closer. 3.19181. See, it's sort of fun. Yeah, you just play around, keep typing it in. Yeah, okay. So I don't want you to, all the bold questions, did they come out bold on yours? Those are all trial and error ones. I don't want you to get too worried about them. I left them in there from advanced functions so you can see what's coming, what happens in advanced functions. Logarithms usually taught as the last chapter in advanced functions. Okay, so we'll keep it moving. When I do the trial and error, I'll do it pretty quickly because I'm really not trying to overteach that today. I want to teach the other parts of it. A vintage comic book is worth $500 and is increasing in value at 15% per year. We got to talk about increasing by 15% per year a little bit. And maybe this is going to come out because Black Friday's coming. I just want to go off to the side and do a little thinking about increasing by 15%.
Is that 1.15?
1.15. Okay, so he's a step ahead of me. Let me talk about this, and maybe you've seen it before. If you go to the store this weekend to buy something and say it's $80, and there's 15% tax on it, there's 2 ways to do that. You could multiply it by 0.15 and get $12, and then go 80 plus 12 is 92. You can do that. But there's a way to get there directly, is to multiply 80 by 1.15. 115% of the price. See, when you go to pay for something, you're actually going to pay 115% of the price. So you can multiply by 1.15 and get directly to 92, and I'll show you on here.
Todd, where did we get the 80 from?
I just made that up.
Oh, okay.
I just said if you go to the store this weekend and buy something that's $80, and you want to know how much tax is going to be on it, you could multiply by 0.15, get the tax and add it on. You can do that. And maybe you want to know the tax, so maybe that's what you want to do. But if you just want to get to the final amount, the multipier's 1.15.
So, because it has to be greater than 1, you can just make it 1.15.
Yes. The B here would be 1.15. So this is the part of the lesson that I'm really here to teach today, is how to deal with percents. And maybe you think that's easy. Maybe you've seen this before. Then great. So now the exponential model is y equals a b to the x. I'm going to stick to my a's and b's. And those of you who are thinking chemistry, biology can see if you want to play around with the c's and a's, which it doesn't really matter which one you use. And so my exponential model here is y equals initial amount and then 1.15 to the x. By the way, we're just now stepping into the business world. So if you're maybe thinking business, economics, those type of things, hey, money example. Now we've stepped out of biology and over to business a little bit. So, nice model. Now I can find the value of my vintage comic after 10 years. I can just sub it in. I can just go y equals 500 times 1.15, 10 times, and my calculator can handle the rest. I can find out what this comic's going to be worth. 500 times 1.15 exponent 10. $2,022.78. Now, I know it's like, oh, like it'll be worth exactly that much. I'll have to sell it for $2,000. I know. The model just tells you this is about what we're talking about, if it's going to increase by 15% every year. It's not trying to claim that this is exactly the amount that it would be sold online for. That's not what it's trying to claim. Now, if you wanted to go the other way, in grade 11, you'd have to trial and error it. You'd have to then go, okay, y equals, no, we want it to come out to be 2,000 equals 500 times 1.15 to the x. And I'll say it again. I have no intention of putting this on the test. There might be one or two in the homework where you got to trial and error, but it's kind of fun. You go over here and you go 500 times 1.15 to the something, and here I've got a pretty good hint. It's a little less than 10, eh? Because 10 was 2022. So let me
9.919.
trial and error. Nathan likes this, yes? He's all over it. Trial and error, x equals approximately, what did you get?
9.919.
Okay.
And it's 2,000.00.
Like right on. He thinks he's pretty good, especially the 2 decimal place. Money's nice because once you get 2 decimal places, you know you're good enough. 2 decimal places, lots in money. So you business people, you don't have to worry so much about decimal places. Okay, so again, the bold ones don't get too wound up about. And again, I'll say it. We're going to teach you logarithms in grade 12. We have a better way than trial and error. We just haven't got to it yet. But the homework might ask you to do that once. Any questions there? Is you okay?
Okay.
Do you want me to show it? He did some, oh, the logarithm. Oh, yeah. Yeah, it's pretty straightforward. Yeah, you can play around with the log button and see if you can get it exactly. So did you do it here? Did you go log? You'd have to do log. Oh, on this calculator, I have to do log 4 divided by log 1.15. And I think I'll get the exact answer here. 9.91868909. So it's not a big mystery to do these. We just don't have enough time in grade 11. So we move it to the grade 12. Because 2,000 divided by 500. I need a multiplier of 4, that's all. Don't get distracted by that. Yeah? Just be aware that logs are out there and coming soon to help you out. She might have to use them in chemistry. If you're taking chemistry, once in a while she's like, you're going to have to press the log button here. I can't explain it right now. But and all she's doing is log trial and errors this for you. It finds the answer for you. Yeah? Mr. Todd's van is worth 20,000. Huh. I wish it was. And it's depreciating at a rate of 20% per year. This is a little more difficult. If it's depreciating at 20% per year, what percentage of its value will it be at the end of the year? Say it again. Let's go to Black Friday again, shall we? Over here. Say you go and you go to buy something that's $200 and it's 20% off this Friday only. You could do it like this. You could go 200 times 0.20, which is $40. You're like, it's only $40. No, $40 is the discount. And then you could take 200 and subtract 40 and get $160.
Can I just use 2.8?
Yes, or you could go 200 times 0.8. I'm going to put a 0 there to help, to say, oh, or you could find just 80% of the price. And that's what you've got to do here, is get a multiplier, and I'll put 0.80. If you look at it and go, can you just, 0.80 isn't it just 0.8? Yes, absolutely. But thinking of it as 0.80 really helps to visualize what's happening here. So my exponential model is y equals, I almost wrote c a to the x because that's what's in my brain. That's what I'll write. If you just let me do that, I'll write c a to the x because that's what I'm used to. But we've been doing a lot of a b to the x, and that's fine. So my exponential model here is y equals 20,000 times 0.80 to the x. Do I need the other 0 there? No, I don't, but it helps. It helps to go, oh, I want 80%. Mr. Todd's van will be worth 80% of what it was at the end of the year, 20% off. And then what's the value after 10 years? And this is pretty close to how vehicles depreciate, by the way. 0.80 to the power of 10. What do we get here? 2,147 and how much? 48 cents. Clearly the 48 cents doesn't matter. I'm not going to advertise it on Kijiji for $2,147.48. But it gives you an idea of where this value is going to end up. Normally vehicles depreciate about this speed. A 10-year-old vehicle will drop this much. It's not happening right now. Due to supply issues and COVID and all that kind of stuff, vehicles are sort of holding their value pretty good. Used vehicles are worth a lot of money. So my van isn't doing this right now, but it probably will as soon as the supply chain gets all fixed up again. So you should be used to that kind of number. What's the lesson? If you like your money, don't buy a new car. Buy a used car because they drop off in value unbelievably quickly. So that's the end of my lesson in advanced functions, or maybe in one challenge homework question. It'll say, when will the van be worth 1,000? So you'd go 1,000 equals 20,000 times 0.8 to the x, and you'd try and play around until you got the number. And I'll show it here this time because Nathan doesn't have the answer yet. So 20,000. I'm going to make a reasonable guess here. 0.8 to the power of, well, it's got to be more than 10 years. So I'm going to go.
11.3.
You already tried it? No, you didn't try it. I'm going to try 15 years. 15 was too many years.
I knew it was 11.
14 years.
Again, knew it.
879. Too many years. 13 years. 1,099. Oh. It's got to be more than 13 years. 13.5 years. 983. Oh, less than that.
13.81.
13.4 years. 1,005. Okay, so I'm going to go with it. X equals approximately 13.4 years. Yeah, you're just playing around until you get pretty close, knowing we've got something better coming. Logarithms is on the way. It's not that it's too difficult. Again, it's not too difficult. It's just time. We only have so much time in this course to teach so many topics. Okay, so chemistry people, you're going to have to wait until we get to logs for you. Questions there in example 3? Getting my sheet out to make sure, time-wise, I'm doing okay. Oh, yeah, I'm almost done. I got to do decay, 2 examples, and we're home. Okay. These were all growth models until the van one. I snuck it in there. You see that? The van got smaller. So the fact that this thing got smaller only has to do with the choice of the b value. If the b value happens to be below 1, this thing's going to get smaller, not bigger. And I just snuck it in there. It shouldn't overwhelm me when it happens. I didn't even mention it was going to be a decay problem. There it was. So I mentioned that in the notes here. I say, well, for exponential decay, use the exact same thing. The only difference is the growth factor is going to be a fraction or a decimal that's between 0 and 1.
This was on the assignment for, well, something like it.
Yeah.
For the,
Yeah. Because it's the same stuff. It's just
I
in
remember writing these
yeah,
lessons,
it's just in word problems. That's all. That's the only difference. So the quantity A sometimes is called the decay factor, and this is what's used. I'm going to show you in a second. Almost exactly the math it takes to find out how old dinosaur bones are. Okay. So if you have questions where quantities are getting smaller, use a decay factor between 0 and 1. Okay, how can this get difficult? I'll show you. I'm going to do a question 2 different ways that's a little more difficult, 1 step more difficult in all these. Special examples with special versions of the model. Another bacteria doubles every 2 hours. Yee. Doubles every 2 hours. This changes completely how you're going to do it. Now I'm going to show method 1, and I'm going to call this the math method. And then over here I'm going to do method 2, which is the science method. Well, not one better than the other, just different in how you'll handle it. If the initial population is 50, find the population after 10 hours. Careful now. I'm going to make the model here. Y equals a b to the x. And y equals, what's the initial amount? 50. So far, this question doesn't look any more difficult than the previous ones. It says it's doubling. So what's the base if I'm doubling?
2.
2. So far, no big deal.
Do we simplify?
It says find the population after 10 hours. After 10 hours, I'm going to put a dot, dot, dot. I'm going to go y equals 50. And I need somebody that's really reading the question and understands what's happening to go, what x value would I use if 10 hours have passed? Here's my hint. 5. Yeah, my hint was going to be it doubles every 2 hours. Why is it 5? It doubles every 2 hours. So how many times has it doubled? Only 5. See, math people will be like, yeah, I got it. I'll figure it out. I don't like this math. I'm a math person. I don't like this way because it's prone to errors. It would be easy to miss. It would be easy to sub in 10, but this double every 2 hours causes you a problem. So I can get the answer this way, and I'll show this way, but I want to show something better, especially for you science people. Yeah.
Doesn't the exponent have to be in the brackets?
Oh, no, it doesn't matter.
Oh, it doesn't?
No, you're right. Other times I did it, and this time I didn't, and I've been called on that before, and I'm glad I make that mistake, but you'll get the same answer either way. Okay? 1600. Here's what the science people would do. As soon as they see that double every 2 hours, they go like this. Y equals A B time divided by 2. They'd build a formula that divides it by 2, and they can just sub the time in. They don't want to be playing around with this. Science people have a lot of stuff to remember, a lot of stuff to keep track of. They got to do labs. They got to do all this stuff. So they make a better formula for doubling or for half-life, both. They build something that has that divide by 2 built right into it. So their formula would look like this. Y equals 50 times 2, and I'm putting the exponent on the outside this time just to show it doesn't matter where I put it. And they build this formula, and they say, let's build a formula that automatically divides by 2 because it doubles every 2 hours. They will like that way better. And then what they'll do is go 50 times 2 to the exponent of 10 over 2, and they'll get the same answer. But I'll put a smiley face over here. You might like that better for those type of situations. Am I intending to trip you up on this, on the test? Not without putting it, look at, I put it in italics here or in bold or something to draw your attention to it. But be aware, going to science, especially chemistry and biology, you're going to see this formula a lot with a little divider in there to go divide by how often it doubles. Yeah? In fact, it's got a special name on the next, in the next box. It's called the doubling formula or the half-life formula. It works for half-life as well. So I want to highlight that specifically. And then do one more example, which is dinosaur bones. But do you have any questions about what I did there? One formula goes, you got to use your brain. You got to go only double 5 times because it's every 2 hours. One goes, as soon as we see the double every 2 hours, let's put the 2 in the formula so nobody forgets. Okay? Very clever, science people. Very clever little formula you've built there. Here it is, formally. Doubling and half-life formula. If it says doubling, you can use this formula. Y equals A 2 to the t over d, where d is the time to double. That will make your life a little bit more convenient to know that version of the formula. The base is already given this time. Time's already filled in. The A is still the initial amount. Pretty nice little formula. It works for half-life too. Have you heard that phrase before, half-life? Maybe you've heard it in a TV show or a movie or something before, but never really talked about it before, but I'm going to deal with it right now. It's not complicated. The half-life formula looks like this. Y equals A, but the base is half, and then I use an H, and the H is half-life. So if you've heard half-life before, but you never knew exactly what they were talking about, here's the example where you get to deal with it. This one says find the half-life. It says the half-life of carbo. Carbo? Does yours say carbo?
It says carbon.
Oh, I corrected yours, but not mine. The half-life of carbon is, truth, 57,030 years. Let's talk about what that means. First, we'll talk about the half-life of Mr. Todd's paycheck. It has a very short half-life. On purpose, I've set up my bills in my account, so my paycheck appears on Thursday, and my mortgage and my car payment come out on Friday. See? Very clever. When I bought my house, I went in and said, make them come out on Fridays. I get paid on Thursdays. Gives me a chance here. Okay? That makes the half-life of my account about 1 day. About half my money disappears the next day. That's what half-life is. How long till half is gone? Carbon, the half-life is 5,730 years. So if something started with 100 milligrams of carbon, say a dinosaur bone, at year 0, at year 5,730, it would now have 50 milligrams. Why does carbon disappear? Well, you better go take chemistry class to find out why. Carbon randomly breaks down, pretty much randomly, into other things and disappears. So when you pick up a dinosaur bone, we can date it almost exactly. I don't mean like, oh, this dinosaur died January 5th, 5,000 years ago. I mean like very close to the year. That's how they can figure out the whole evolutionaries. They know exactly how old something was. Yes, they can account for if it's in the ocean or underneath rock. They can take care of all those things. Okay. So explain half-life. It is known that a certain dinosaur bone will start with 4,000 milligrams of carbon. How would we know that? We just study. There's lots of bones out there. There's lots to study. So if you know they're starts with 4,000 milligrams, how long will it take for the amount to reduce to 500? This isn't quite paleontologist stuff yet. This is what we can do without logs. We can do a question where it's like, okay, y equals a times 1/2 to the t over h. But we know a bunch of stuff. We know it started with 4,000, so we know the A. And as promised, most times we give you the initial amount. Now, 1/2, most times you'll just go ahead and use 0.5. That's totally allowed. And if we want to get the carbon down to 500, then we got to figure out this T. Now, this is technically a grade 12 question. How long is the half-life? 5,730. This is technically a grade 12 question because the unknown's up here. I'd have to trial and error this. The ones in your homework, they'll give you the time and ask for you to get the amount, so you'll just plug it in. But this is one that goes the opposite way. So then we have to play around. Ooh. And the reason I did this one is I believe there is one in your homework where you got to do something like this. So you got to go 4,000 times 0.5, and then up in the exponent, t. What's my guess here? 10,000 years? I don't know. I wouldn't even know how to explain what to guess. But I'll try 10,000 years. Maybe this bone is 10,000 years old. And I put in 10,000. And what am I hoping for when I press equals? 500. 1193. I didn't choose a big enough number. It didn't get down to 1193. It must have been older than that. Is this exactly what paleontologists do? Pretty close, actually. They just use logs to do it, that's all. 15,000 years was too long. Maybe 14,000 years. Oh, I hit 4 again. Or I hit 5, yeah. 14,000 years? 735? No. I forget where I was. 14,500? No. Which way was I going? 13,000 years? $13,000 years? 830? Oh, that's getting closer now. 12,000 years? Oh no, I'm trying to get to 500. I lost track there. 14. I'm trying to get down to 500. So that more than 14,000 years. 14,500 years. $14,500 years. 692. I'm trying to get down to 500. 14,800 years. 667. More. Why didn't I go over 15,000? Is it more than 15,000? 16,000. 577. Oh, it's more than 16,000 years. 16,500 years. Oh, getting close now. 16,800 years. Real close now. 16,900 years. Real close now. 16,950 years. See, now I'm just having fun. Ooh, 980 years. Does it go all the way to 17,000 years? I don't know. Let's go up to 980 years. 16,980. I need that 5 out of there. 512. It is. It's over 17,000 years. I thought it wasn't. And I'm doing the best I can here, folks. I'm doing a sales pitch for logarithms here. That who wants to be playing around like this? It's over 17,000 years. I didn't think it was. 17,800. Let's jump ahead. Okay, now I've got it narrowed down. Now I can Prices Right this thing. Do you know what I'm talking about? Do you watch the Prices Right?
Yes.
17,400 years. 17,600 years. 17,400 years. Stop that. I'm busy. 17,100 years. 17,000, trial and error. T equals approximately 17,190 years. But you can get as accurate as you want and really knock this down to a specific era in the dinosaur ages and know exactly when that dinosaur existed and when it died away. And then you can find all the dinosaur bones of a certain type and find out when that dinosaur went extinct, because we don't find any more dinosaurs like that. Yeah? Question? It does have a limitation that this whole, it has limitations all over the place. But when you get enough bones in enough situations, it's not hard to get it all mapped out. Yeah, yeah. So, and those gaps get filled in all the time. They find a new bone, they find a new fossil, and they're like, oh, here's a gap we didn't know about. We didn't know how this evolved to this. Now we do know how it evolved to there. So those things fill in pretty quickly. Yeah. And, well, yeah, and so depending on where they're found, they might have to use a different number there. Yeah, okay. Okay, was that the last example? You're not going to be asked to trial and error much. Basically, you build the equation, you get to sub in the t. You'll find it much easier when you don't have to get the t value. When they give you the t value, you just plug it in. Like, okay, let me go back. Just in case that last example did confuse you a little bit. This is more like what you'll have to do. They give you the t and you just sub it in and get the answer. You know, you won't have to go through what I went through in the last one.